I am Rajeshan, working as an assistant professor in the Department of Electronics and Communication, Maharaja Institute of Technology, Mysore. The course we would be studying in the forthcoming sessions is the VLSI lab. As you can see, VLSI stands for Very Large Scale Integration, and the course code is 17 ECL 77. We will see the course objectives in the VLSI lab. It deals with the computer aided design tools or CAD tools. We will be seeing the custom IC design flow. We will learn what do we mean by the DRC, design rule check, LVS, layout versus schematic, and we will design and simulate the digital circuit, and also we will design and simulate the analog circuit. The course syllabus is divided into part A and part B. In part A, we do have the digital circuits, and the simulation tool for designing the particular digital circuits is the Xilinx, and the experiments are how to design an inverter, how to design a buffer, how to design a transmission gate, basic and the universal gates, flip-flops, SR flip-flop, JK flip-flop, D flip-flop, T flip-flop, master-slave JK flip-flop. We will design a parallel adder and serial ladder. We will design a synchronous and asynchronous 4-bit counter. So, this is the digital circuits we would be designing, and in terms of part B, which is analog circuit, the simulation tool that is used is microwind. We will design an inverter, we will design a pseudo NMOS inverter, we will design a common source and common drain amplifier, we will design a differential amplifier, we will design an op-amp, and at last we will design an R2 to R DAC. When we see the experiments of the digital circuits, we had already studied in the theory subject, which is in terms of Verilog HDL. In Verilog HDL, as HDL stands for hardware description language, and we specifically the common two languages are VHDL, very high speed integrated circuit hardware description language, and Verilog. When we just compare the Verilog and VHDL, the Verilog requires fewer number of instructions rather than VHDL, and in this course we will be writing the instructions or the program in Verilog rather than the VHDL. And in part B, which is in terms of the analog design, the simulation tool we have told is the microwind, and we have studied how a MOSFET works and the fabrications of the particular MOSFETs. Either you call it as an N MOSFET or you call it as a P MOSFET, and also we have seen how to write a particular stick representation or stick diagrams and the layouts in the theory subject, which is the VLSI design. So, basically we will write the stick representation and the layouts in terms of the analog design, which is in terms of part B. When you just see the part A and part B, the basic practical applications that we would be seeing is in terms of the processor. So, if you just study part A, we will define the instructions or the programs, and which is related to the applications of the particular microprocessor that is used, and in terms of the part B, we will design how the circuit would be working, and the practical application is your CMOS sensor, which is called as a complementary metal oxide semiconductor sensor. So, we will start with the experiment. The experiment 1 we will see is how to write a Verilog code and a test bench for the inverter. You can just see here a Verilog code is written, and next to see the simulation results of the particular inverter, we are writing the test bench. As we have seen in digital electronics, a digital symbol of NOT gate. A NOT gate contains a single input and a single output. Let us define it as an input with a variable A and an output with the variable B. Suppose if we just provide a digital logic of 0, then the output would be a complementary function which would be 1. If you just see the particular truth table of the NOT gate, we have defined the input as A, the output as a variable B. If you just provide input of 0, then the particular output is 1, and again if you just provide input of 1, we would get a complementary of output which is equal to 0. So this is with respect to the digital symbol with the digital electronics. And if you come to the MOSFETs, which stands for metal oxide semiconductor field effect transistor, we do have two types of MOSFETs, which is called as PMOS, and another one is the NMOS. And the digital representation of the particular PMOS is defined, and it contains terminals of source, gate and drain, and you can just see the particular bubble that is defined at the gate end, which would mean that we need to provide an active low input. Next, it is of the NMOS. This is the digital symbol of the particular NMOS, and the terminals which are defined it as drain, gate and source. By combining the PMOS transistor and the NMOS transistor, we do get another type of transistor which is called as CMOS, which stands for complementary metal oxide semiconductor, which is a combination of PMOS and NMOS. So we will write the digital symbol of the particular PMOS. Let us define the particular PMOS, and we will define the NMOS, and we will write the terminals source, gate, drain, gate and source. The gates of the particular PMOS transistor and the NMOS transistors are shorted, which is provided by the particular input. Let us define it as Vin, and we will just define with a variable A, and the drains of the PMOS and the NMOS are shorted and is taken as an output. Let us define this as V out, which is Y, and we will have two supply voltages, the source terminal of the PMOS is connected to a supply voltage of VDD and the source terminal of the particular NMOS is connected to ground or VSS. So this becomes a digital symbol or a digital circuit of a complementary metal oxide semiconductor, which is a combination of the particular PMOS and the NMOS. So we will just see the functioning or the working of the particular CMOS transistor. We will take variable A, that is defined as the particular input, and variable Y, which is defined as the particular output. So we will provide a digital logic 0 to the input of the particular CMOS transistor, and we have told that the bubble in terms of the PMOS transistor acts as an active low input, or it takes active low input. That would mean that this particular PMOS transistor is on and it is a closed switch now, and the NMOS transistor is off and it is an open switch, and whatever the value that is present here at the VDD, it is moving through the PMOS transistor and it is obtained at the particular output, and we will define it as a digital logic 1. So if we provide the input as 0, the PMOS transistor is on and the NMOS transistor is off, and the output is high, which is equal to 1. So if we provide input of 0, then the output is 1, and we will see the next operation. Again we will provide input of 1, then the particular PMOS transistor would be an open switch or it would be an off state, and the NMOS transistor is an on state. Whatever the voltage that is present across the output, we have told that it is a digital logic 1, it is sourced towards the NMOS to the ground, where the NMOS is a closed switch, then the particular output would be 0. Suppose if the input is 1, then the particular output is 0. So input is 1, then the output is 0. So you can just see by the particular truth table, when we just provide input of 0, the output is 1, and the input of 1, the output is 0, which is done by using the combination of PMOS and the NMOS transistor, which is called as a complementary metal oxide semiconductor, and which is defined by the particular NOT gate of the operation. So we will write a Verilog code for this particular inverter, and we will see the simulation results by writing another Verilog code which defines the functionality, which is called as the particular test bench. So for writing the Verilog code for the particular inverter, it starts with module which defines the functionality that we are writing the code in Verilog, followed by the name. Let us define it as INV, followed by the ports list. As we have seen the particular circuits where we have defined the input as A and the output as Y. Next we will define the port declaration, an input of A, and the output as Y, and we have told that the inverter is a NOT gate or a complementary metal oxide semiconductor, where we would be having a complementary function which is followed by a particular instruction in HDL which is called as an assign, which means it is a continuous assignment statement which defines the value on a net, and Y is equal to complementary. So this is the operator which defines the complementary function of A. And we have started with module. We need to end the particular functionality where we do have the end module. So this is the Verilog code for the particular inverter. Next, to see the simulation results or the functionality of the particular Verilog code of the inverter, we will write the test bench. Again, we are writing the particular program in Verilog. It starts with module followed by the module name. We will define it as inv underscore tb, which is called as test bench, followed by the inputs and the outputs. What we have told it as port declaration, and in writing the test bench we are defining the inputs as reg, which means that it is a register which is a storage value where the value of a particular variable is held, and we have defined it as A. Next, we will define the output, which is a wire where the value of a variable is sent to a particular output which is defined by wire or net, and we have told it as Y. And the next instruction is module name, it is written, and followed by a particular instruction which is called as UUT, which stands for the unit under test. We are testing the Verilog module to define the simulation results. So we are interlinking the Verilog module with the test bench of the inputs and the particular outputs. So again, interlinking, we have defined A of the Verilog code, and we will define the test bench input which is defined as register. Next, the output of Y we have defined, and output with respect to the test bench we have defined it as wire, which is Y. So this is the instruction which is called as an unit under test. So where you are testing your Verilog code for the simulation results, and we are initializing the process with initial begin, and next we will define the inputs for the particular inverter. So we have a variable which is defined as an input, and we will define the inputs as 0, which is 1 bit of the value, and the value which is assigned is 0. So that would mean that your simulation starts from 0 and the value assigned is 0. Next, after 5 seconds, that would mean that from the 6th second the input value changes. What we have told it as hash phi, and we will define another input as one bit of the representation, and the assigned value is 1. So 0 to 5, the value of the particular input would be 0, and from the 6th nanosecond the value changes to 1, and we can define n number of inputs. According to the n number of inputs, we would be obtaining the particular output, which is a complementary functions. Again, we will have 2 more inputs. For 5 nanoseconds, the input changes to 0, and for another 5 nanoseconds, the input changes to 1. So we can have n number of inputs. So we have initialized, we will end the process of the particular inputs, which is an end, and we will stop the process where we have started the functionality with module with the end module. So this is the Verilog code and the test bench for the particular circuit, which is an inverter.